Alright, so I'm going to go over the solutions to the thermal energy unit review problems before your test tomorrow. This will be quick. This should be around a 12-minute video. So here, if you put in on one flask some food color with 150 ml of water and then 1 drop of food coloring into each flask, what you might see is something like this. So the drops of food coloring going into the flask and the water below and sinking to the bottom of the flask itself. After some time, what you'll start to see is the formation of convection currents in the water. And this is a phenomena where warm water rises. This is convection. And so you'll see flows. Really all you need to say here is convection, warm water rises. Okay. In terms of kinetic energy of the molecules and particles of the substance, what is happening when the temperature rises? If the temperature goes up, then average KE of molecules goes up. Temperature goes down, average KE of molecules goes down. It's nothing too complicated. Temperature is just the measure of the average kinetic energy of the molecules. And that's what question number 3 is asking as well. Temperature. Now, if you have 2 beakers of water with different amounts of water, after 5 minutes of heating on the same heat source, beaker A is at a higher temperature than beaker B. What is true about their masses? Okay, so A, B. If A is at a higher temperature than B, then clearly A had to have less water if they're under the same heat source. Because if they're under the same heat source, the temperature of this beaker is going to be a lot higher than the temperature of this beaker. Because there's more mass here, right?
Two different substances of the same amount are heated over the same heat source. Substance Q records a change in temperature of 50 degrees Celsius and substance S records a change in temperature of 12 degrees Celsius. Explain why this is the case. Okay, same amount, so they have the same mass, same heat source. Substance Q has a change in temperature of 50 degrees Celsius, substance S records a change in temperature of 12 degrees Celsius. So clearly substance Q has a bigger change in temperature. That means one good way of looking at all problems that are like this is to write down this formula, Q is equal to MC delta T. And notice that the change in temperature depends on, remember, the amount of heat that you add, the mass of the substance that is being heated up, and the specific heat capacity of the substance that's being heated up. So if you have the same mass and the same heat source, then the difference has to be that the specific heat capacities are different. And if substance S has a smaller change in temperature, substance S has more resistance. Substance S has more resistance to change. Substance S has more resistance to change in T / higher specific heat. Silver has a specific heat capacity that is almost twice as much as gold's. Equal masses of silver and gold are placed on the same heat source. Compare the change in temperatures of the wire and explain. So if silver has a specific heat capacity that is almost twice as much as gold's, so silver has way more resistance. Silver has more resistance because it has a specific heat capacity that's twice gold's. Silver has more resistance, therefore it changes temp by half as much. 2 times as much resistance, for it changes the temp by half as much.
So on the diagram to the right, which material would have the largest change in temperature if 1,000 joules of heat was added to it? Largest change in temperature would be the smallest specific heat. For all of these, the smallest specific heat is diamond. The diamond has the least resistance. Smallest change in temperature would be the one with the largest specific heat. So probably helium. So that has the smallest change in temperature. Now, the other questions that we're asking are whether or not we have these 4 different spoons, and for each of these spoons we know that they are going to reach thermal equilibrium if they're placed in equal cups of hot water. Now, what is it called when the spoon and the water reach the same temperature? This is called thermal equilibrium. Define this and explain in detail what this means for heat transfer. Heat transfer stops. Which spoon will have the greatest change in temperature once it reaches this point? That's a good question. If they're all starting at 20 degrees Celsius, this is starting at 20 degrees Celsius, 20 degrees Celsius, 20 degrees Celsius, because they all start at room temperature, right? And if they are all placed into separate but equal cups of hot water, 85 degrees Celsius, they're all going to reach the same temperature as their surroundings, and so eventually they're all going to reach, it doesn't matter whether or not one of them is bigger or smaller, they're all going to reach the same temperature of 85 degrees once they get put into the cup of hot water. So the answer to questions 2 and 3 is none. All will have same change. Some will have more heat transferred to them, which is an important point. Some will have more heat transferred to them, but all will reach the same temperature. So the difference between the temperatures will be the same. Okay, so as the substance is heated, circle all the possible changes that will likely occur. Okay, so if the substance is heated, the kinetic energy of the molecules increases, correct? Specific heat, kinetic energy definitely doesn't go down. The specific heat does not change. The temperature of the substance will likely increase. The temperature of the substance will definitely not decrease. Specific heat, remember, doesn't change because it's fixed for each substance. If the temperature goes up, then the average molecular speed of the substance will increase. The mass will probably not change. So mass and specific heat stay the same. Kinetic energy, temperature, and speed will all increase as the substance is heated. Cup of hot soup is placed in a large room where the temperature of the air is 20 degrees Celsius. After a few hours, the soup and the room are in thermal equilibrium. Explain the transfer of thermal energy in the final temperatures of the room and the hot soup. So the thermal energy will transfer from hot to cold, the soup to room. Both will eventually be at a common temperature of 20 degrees. So the temperature of the room is not going to change really because it's a big room, and that it's not going to be affected by just a cup of hot soup. But the hot soup is going to lose its thermal energy to the colder room around it. So the cold air is going to literally steal the thermal energy away from the hot soup, and so the thermal energy is going to transfer away from the soup to the room, and eventually they'll both be at the same temperature. These questions 11, 12, and 13 require you to use Q is equal to MCT.
So for each of these, the boiling temperature of steel is 1510 degrees Celsius. How much energy is required to bring a 1,200 gram from room temperature to its boiling point? Okay, so we need to know how much energy. So we are looking for Q. We are definitely looking for Q here. And we know the mass is 1200 grams. We know the specific heat is 0.12 joules per gram times degree Celsius, and we know that the change in temperature is the difference between 1510 and 21, because the change in temperature isn't 1510. If it was starting at 0 degrees Celsius, then it'd be 1510. The change in temperature is the difference between 1510 and 21. 1510 minus 21 is equal to 1489. At this point, all we have to do is multiply these three numbers together. So we got 1200 times 0.12 times 1489. That gives us 214,416 joules. It takes 12,040 joules to heat a 1,300 gram stack of newspapers from 30 to 35 degrees Celsius. What is the specific heat capacity? So now we're looking for C. Got to do some algebra to get C by itself. We got M and delta T on this one side. To get C by itself, I'm going to divide both sides by M times delta T. So at the end we have Q divided by M times delta T. Q in this case is 12,040 joules. M is 1,300 grams. Delta T is 30 to 35, so 5 degrees Celsius. 12,040 divided by 1,300 times 5 gives you 1.85. And then the units are joules per gram times degrees Celsius. Why are those the units? Because look, when we divide joules by grams times degrees Celsius, that's what we get. Alright, final question. Oh no, we have two more questions. 400 gram block of gold is at 15 degrees Celsius. If 5,490 joules of thermal energy is added to the block of gold, what is the new temperature? So we know that we're looking for the change in temperature. So delta T is equal to Q divided by M times C. In this case, Q is this 5,490. The mass is going to be 400 grams. The specific heat capacity is going to be 0.129 joules per grams times degrees Celsius. Now, when we multiply all this out, 5490 divided by 400 times 0.129. That gives us 106 degrees Celsius. Now, here's the thing. This is the change in temperature. This is asking us for the new temperature. Now, this, we know that it started actually at 15 degrees Celsius, and the change in temperature is 106 degrees Celsius. So the final temperature is actually going to be 15 plus 106. (121 degrees Celsius). Okay. Explain the three different forms of heat transfer and provide 3 examples of each, total of 9 examples. Explain how you know each of these examples is the method of heat transfer you identified. Alright, we gotta be a little creative here. So, start with conduction. So, this is via contact. Direct contact between two objects. Convection via circulation through liquid.
Could I have your attention, please? Just a reminder, the SILT meeting is being held
liquid
in
or
the
air.
Gold House Teaching and Learning Suite.
And then
the SILT meeting is being held
finally,
in the Gold House Teaching and Learning Suite. Thank you.
Via
electromagnetic waves. Alright, so we want 3 examples of conduction. I can think of one right now. So my hand is touching on the surface of this table. What if the table was hot? What if the table wasn't a table? What if in fact it was a stove? Oh, look at that, we have an example. We got a stove top. It's got like a little grill on it. So, wow, that's a terrible stovetop, but you know, it is what it is. It's a grill. If you have something sitting on the stovetop, that is conduction. It's directly touching. We'll call that a tea kettle. Tea kettle. Also, if you have a spoon in a cup of hot water, another example of conduction is if you crack an egg on a pavement. It's the pavement. If you crack an egg on a hot pavement and start to sizzle. I'm really uncreative, I'm sorry. That's conduction. Anytime you have direct contact or direct energy transfer from one surface to another. Okay, convection via circulating through liquid or air. A really good example is in water, in the ocean, where you have warm water that circulates up, and then you have cold water that rises, or that drops. Right? Or this is in the ocean. Or if you are in a house, right, and you have a house that also has warm air rise and cold air drop. And another example, final example for convection might be if you have, let's say, wow, I really can't think of another example right now. Totally can. Pot of water. No, that's the same one as that. Wow. Campfire. So you have a campfire. When you have a campfire, you're going to feel the heat directly above, and the heat from the campfire is going to circulate up. It's going to rise. And then the cold air is actually going to fall on the sides of the campfire. I'm going to draw the campfire. I'm going to draw the radiation once I'm back because there's really not much space here. Radiation, some really good examples are obviously radiation, from the sun, because the sun radiates out electromagnetic waves, UV waves. Another example is on the Earth, if you've ever used a microwave. Beep beep, and there's like all the numbers on the microwave. Whatever. Microwave! Inside the microwave it works because it's actually shooting microwaves from side to side. And this is what, the rotating microwaves is what heats up your food. Radiation. And a final example is actually if you're in a tanning bed. Tanning beds work in the exact same way as microwaves, literally. If you go inside a tanning bed, the reason you get tan is because your the UV light inside of the tanning bed actually promotes, I'll call this tanning bed. The tanning bed actually shoots out UV waves in the same way that the microwave does. And what the UV waves will do is actually stimulate your skin cells to produce something called melanin, right? And it does this by stimulating melanocytes. And this can be bad in the long term because what it might do is overstimulate melanocytes and then cause overproduction of melanin as well as burning, right, on your skin.
because the UV can actually damage skin follicles if exposed for a long period of time. It can also cause cancer by causing double-stranded breaks in your DNA. A lot of reasons not to go tanning. We could do a whole lesson on that too. But for now, watch this video, slow it down for your test. You guys are going to do great. Let me know if you have any questions.
Please come to the
Bye.
main office. Vincent Coopin, if you're in the building, please come to the main office.